1, 2, 3, go.
Hello everyone, so today in this video we will discuss about this crystal structure. So my group had 3 members. So crystal structure include three of the structure inside. So we have 5 essential qubit is called FCC, body central cube is BCC, hexagonal closed path is HCP. So firstly I will demonstrate the FCC 5 central qubit. So it's very popular in the real life. It's included in the nickel, platinum, lead, silver, and aluminum. This is a general structure. You can have a look at it, and we will investigate this in the next slide. So atom in unit cell. What's the atom in unit cell? It's a number to help us to calculate the APF is the atomic packing factor. Is really important number to help us to compare with the other material. So we have we need to detect what in the unit cell. So unit cell is all the qubit here. So it have a 6 phase. So one phase we have 1.5 atom. So why we take that 1.5 atom? Because we have the ball, and here we have the ball. We cut half. We cut half up by the phase. So we have 1, 2, 3, 4, 5, 6. So I label everything at here. You can understand it very quickly. So we have 6 phase and 1.5 atom. So we have 6 times 1.5. This means 3. We have 3 atom in here. So we have, but in this one we need to calculate in the atom in the corner. So we have a corner in the qubit. So a corner is label 1, 2, 3, 4, 5, 6, 7, 8 over there. So we have a corner, but why we just take 1 over 8 atom? Because the atom we just made the corner in the corner is here, and then we put the ball inside, and it just shut a little bit. It just shut 1 over 8 of the ball. It's 1 over 8. So we have A and 1 over A. We A times 1 over A. We have 1 more atom, and then we have 4 atom per unit cell. So the next one I'm going to show the atomic packing factor. So to calculate atomic packing factor, we have to know the volume formula and to calculate the volume of total unit cell, total atom per unit cell, and the total volume of unit cell. So this one will divide. This one will have the numbers here, but we go the first. So to calculate, so the unit atom per unit cell we have 4. So we just calculate already. So to calculate the volume per atom. So we need to know the radius. So how to get the radius? So we look at here. This is the phase of the qubit I explained before. So I put it in 2D. So we from here to here is 2 square A, and from here to where is equal 4 radius. So we put in equal equation. We have the equation. We release the A radius equal to 2 square A divided by 4. Then we put everything in here. So we have A power 3. A power 3 will simplify with this one. So the A power 3 will cancel. So we have all the number here will divide by 1. So this one will release this number here. So this the atom packing factor for the FCC structure is 0.74. So if we use this factor, we use this number to compare with the other number for BCC. For example, BCC we will have the other number. We will compare it to get the good material or bad material. So Tom will discussing for the next structure. So thanks.
My name is Tuyên, and today I will discuss about the body central qubit, or we can just call it BCC. First of all, BCC is just a type crystal structure in metals, such as anthracite, chromium, or platinum. In this structure, we have, as we see in the diagram, we have one atom. This is the middle of the unit cell, and then we have like 1/8 of an atom in each of the corners of the cubic. Alright, so in total we have 2 atoms per unit cell, and the BCC structure, it just has no closed planes, and therefore it doesn't have any stacking sequence as well as the stacking force. And we see there's like the central atoms touching, like not touching the edge, but is it touching 8 other atoms in its corner of the cube. So the coordination number for the BCCs is the number of atoms touching atoms, right? So the coordination number is 8 for BCC. To move on to the next slide, have a look at this diagram to help you have a better understanding with the atomic packing factor of the BCC. We had to look at the diagonal cut through the unit cell. Based on that one, we have the relationship between the radius of the atom and the length of the edge of the cubic. We have R equal square root 3/4 of A, and we have another formula for APF is the volume of the atom in unit cell per divided by the volume of the unit cell. Altogether, we have the final atomic packing factor for BCC is 68%. This means that the atoms in the BCC structure, they occupy 68% of the volume of the unit cells. So that's it. Thank you for listening.
Hi everyone, my name is Alvin. I'll be here to talk about the HCP crystalline structure. HCP stands for hexagonal close-packed crystalline structure. There is 2 models for the HCP Daniel. This is the 3D projection, and that's the 2D projection. As you can see from the 2D projection, the light green stands for the top layer, the blue stands for the middle layer, and the dark green stands for the bottom layer. And I'll be explaining to you guys how we get all these numbers on the whiteboard down here. In order to figure out the atomic packing factor, we will need to take a closer look at the crystalline structure, which is drawn over here. We have drawn the unit cell for the HCP down here. This is how the crystalline structure looks on a bigger scale. So as you can see, there are 12 corner unit cells and 2 face cells and 3 cells within the unit cell. Now we can give this dimension as C, which is the height of the HCP, and also we can give this as A, which is the length of the hexagonal on the bottom face. Also, as you can see, these 2 atoms will be touching in the crystalline structure, so you can have A equals to 2R. So we will be using these formulas and these 2 formulas to work out the APF, which is the atomic packing factor, which equals to the number of atoms times the volume of one atom divided by the volume of the unit cell. And we have simplified this formula into the one down here. Now if you use the values of C and R cubed and substitute it into this formula, we should get something like this. also Z equals to 6. So if you substitute that in here, you get 6 divided by others. So if you basically factorize this, 6 gets cancelled out with 6. And then A3 gets cancelled out with A3. And then if you factorize all this, you should get 4 times pi times 4 times root 3 divided by 3 root 3 times 2 root 2. And if you put this on a calculator, you should get the atomic packing factor as 0.674. So this shows that how we get the atomic packing factor as 0.674.